Hi. The next rule we are going to deal with here is called the chain rule. And look, when do we need to use this rule? Look, imagine a situation like this. Let's just say that z is some function of y. And at the same time, y is some different function of x. Now, let's just say that we are interested in what is happening to z as x is changing. But how can we do it as x is not appearing in this function? Well, actually, it is, right? Because I could substitute g of x inside of y over here. But let's, instead of doing this, let's just analyze the chain of causality that is going to going to happen over here. So look, if x is changing, it influences y. So it will create a change in y through function g. Then, when y is going to change, this is going to induce change in z through function f. Okay, so look, what we see over here is that when x is changing, then y is changing, right? And when y is changing, z is changing. And we can use this this chain of causality, let's call it like this, in order to find the derivative of z with respect to x. Now, how do we do it? Okay, let's remind ourselves again the definition of derivative. Look, we get that derivative by definition is limit with delta x approaching 0 out of the difference quotient delta y over delta x. And look, we said that when x is changing by this extremely small amount, we call it a differential. Okay, let me remind you a little bit about differential. Imagine that here we have values of x, and x is at some point x0. We remember that this point is so tiny, it doesn't even have a mass. Now, if x is increasing to another point that is right next to it, so they are touching each other, so we get what we could say is basically in between them dx. Because look, here we are having a change that is so tiny that we are basically staying in the same place because none of these points have a mass, right? So we move by so tiny distance, we call it infinitesimally small, that we are staying almost at the same place. Now, if x is changing by this extremely small amount, right? Then, regardless what is the specific form of function g, as long as it's not turning any point into infinity right away, the change in x will going to induce also an extremely tiny change in y. Again, we are moving from a point, but basically we are staying at the same point. So, what we have over here is actually ratio dy to dx. Right? And look, this is nothing more than Leibniz notation of derivatives, which actually is a definition of a derivative. It's a ratio of an extremely tiny change in y to an extremely tiny change in x. Now, So we get another differential here, delta, I'm sorry, dy. Now, but if y is changing by an extremely small amount, then through function f, z is also going to change, and is also going to change by extremely, extremely tiny amount. So what we get over here is that we can work with three differentials. Now, let me just, before we get into the chain rule on its own, let me just now describe to you what is a differential. And it's now better seen as we have this over here. Look, I hope nobody's going to disagree that dy over dx is equal to dy over dx, right? We have exactly the same expressions on both sides of the equality sign, so they must be equal. Now, what will happen here if I'm going to multiply both sides by dx? Let's think about it for a second. Look, if dx would be 0, again, this equality would hold because we would have 0 on both sides. But we know the differential is extremely tiny, but it's still bigger than 0. So definitely we're not going to have zeros on either side of this equality. Okay, so what is happening over here? We are getting dy here and expression dy over dx times dx. And look, this expression that you see over here is a differential as well. This is differential of y. But look, now we've got a connection between the differential of y and differential of x. Because, look, if x is changing by some very, very small amount, then y is also changing by a very, very small amount. But now we have a measure, actually, of those two amounts. Look, it's derivative that we can actually calculate. So look, we can, for example, write that if the function is y equals 3x squared, oh, let's start with something simple, plus y, right? Then, what is dy? Now, dy is dy over dx times dx. So, dy is derivative of this. Derivative of this is equal to 3, right? Times dx. So look, we see that every time x changes by some small amount, y is changing by 3 times as big amount, right? This is why the ratio of the two is equal to 3, right? Again, now if I divide both sides by dx, which again I can't do because we know that dx is different than 0, we are simply getting the formula for derivative, and we see that this is 3. Okay, look, that was of course the easiest possible example because we were dealing with the linear function. But look, now look, even if this would be 3x squared, we would be still able to calculate the differential. How? Look, again, we would use the same formula. We would have the dy is equal now to 6x dx. And look, the difference between linear and quadratic function is that linear function has the same slope, right? It's a straight line. Quadratic function is increasing, and it's increasing, let's just say with the, when we move to the positive values, it's going up faster and faster and faster. So actually, as you see over here, the value of the value of the differential, so changing y, depends on whether x is positive or x is negative, and what is the actual value of x. Okay, but I hope at this moment you get the gist of what differentials are. And look, if we know what differentials are, maybe we can start playing with them a little bit to deal with our case that we've got over here. And look, the case that we have with the chain rule goes like this. Z is some function of y, and y is some function of x. Here we see the chain of causality, and now we are interested in what is going to happen to z as x is changing by small amount. How can I write it? Well, look, we are simply looking for derivative of z with respect to x. And again, I hope nobody is going to argue with me if I'm going to say that this is equal to dz dx. Okay, so we see that both sides of this equation are equal to one another. And now, what can we do with this to get something useful? But still, we need to maintain that both sides of this equation are equal to one another. How about I multiply both sides by 1? Okay? So we've got dz dx. Oh, you know what? I'm going to multiply just one side by 1, right? Because any number, any value multiplied by 1 is the same value, right? So actually, in this case, nothing has changed, right? We still have the situation in which this equality holds. Okay, so this and both sides of this equation are equal. Now, I hope you remember that when we were showing proofs for different rules, we were using some tricks. For example, we were using a trick that we were adding 0, which is always also permitted. And I told you that 0 can be written in different forms, like 4 minus 4. It's also 0, it's just written different way. And look, we can do exactly the same trick with 1. Because if I'm going to take any number, and I'm going to divide it by the same number, assuming the number is different than 0, I'm going to get 1. So, in other words, I can replace 1 by dy divided by dy. It's still 1, right? But look, here we have just some multiplication of fractions. Of course, but in these fractions we have differentials. So why not put this whole thing in just one fraction? Now, we know that unlike in the case of matrix algebra, in regular algebra, it doesn't really matter in which order we multiply. A times b is the same as b times a. So why not use this trick over here? Now we can write that dz dx is the same as dz times dy divided by dy times dx. And what do we get out of this? Now, look, let me just divide it into two separate fractions. And what will I get over here? That dz x is equal to dz dy multiplied with dy dx. And actually, this expression that you see over here is already a chain rule. The chain rule that we're going to be using to solve this problem is this. What do we need to do? We need to find derivative of y with respect to x. And we need to find derivative of z with respect to y. We need to multiply them by each other. And then we're going to get derivative of z with respect to x. So look, here in other words, we could say that we will be calculating derivative of function y. And we're going to be multiplying it by derivative of function x. And this, in a nutshell, is the entire chain. So look, actually it's proved it's way easier than the ones we had before, but of course, before we could get into it, we needed to add some knowledge about differentials and how do they work. Now, let me point you one thing in the formula. Look, we've got here that dz dx is equal to dz dy times dy dx. Look, we said that there is a chain of causality over here. And actually, this chain of causality exists within this example as well. Why? Look, if x changes, then y changes. This change is described by this derivative. But then, if y changes, we expect z to change. And by how much z is going to change? By the value of this derivative. And look, because we've got this chain of changes, this is why we call it the chain rule. Okay, so now let me show you an example that will illustrate how this change is going to work. How this rule is going to work. So look, let's just say that we've got a function z equal to 3y squared, and we've got a function y equals to 2x plus 5. And look, what we are interested in is to find derivative dz dx. And look, from the chain rule, we know that this is going to be equal to dz dy times dy dx. And look, so it means that now I need to calculate derivative of z with respect to y. Very easy, right? 2 goes up front. I get that this is 6y. And then I need to calculate derivative of y with respect to x, which is simply 2. And look, out of this, I'm getting that this is 12y. But this is not the end. Look, I also know that y is equal to 2x plus 5. So why not substitute it over here? What am I going to get then? Well, I'm going to get that this is 12 times 2x plus 5. Or simply 24x plus 60. And this is derivative that we were looking for. dz dx is equal to this. Okay, let's do let's do another example. Let's just say now that z is equal to y minus 3 and x is equal and y is equal to x to the power of 3. Okay, again, we can deal with this case differential, we know that dz dx is equal to dz dy times dy dx. So dz dy, so derivative of z with respect to y is just 1. Right? Then we multiply it by the derivative of y with respect to x, which is 3x squared, which is equal to 3x squared. And we found this derivative. Okay, but look, when we use the chain rule, our primary interest usually is associated with calculation of complex derivatives when the derivative is very complicated. In a sense, it's really hard to calculate using any rule that we learned this far. And let me give you an example of this. Let's just say that y is equal to 3x to the power of 3 minus 2x squared plus 7. Well, if this would be the case, calculating derivative is trivial. But what about if this whole thing is taken to the power of 100? Well, you can say we can use product rule, but then remember, with the product rule, we would have a lot of expressions. Like if we want to use a product rule, technically we would get 100 expressions, each composed out of 100 expressions. Of course, in this case, we could organize them in a very smart way if we figure this out. But in general, it doesn't need to be that easy. Now, look, in cases like this is when we use the chain rule. And I'm going to show you two ways in which we can use the chain rule. The first one is a longer one, but it will illustrate you how the mechanics of this work. But then I'm going to show you the simpler version, how you can do it fairly fast with just two moves, basically. Okay, but look, let's go back to this case. Look, here we've got a case that y depends on x, right? So when x is changing, y is changing. And look, what we are looking for in this case is derivative dy dx. But look, here we know that the function that we've got over here is very complicated. So why not introduce a variable that would make this function simpler? What variable? Look, I see clearly that I have a problem with taking this expression to the power of 100. But I would never have a problem taking x to the power of 100. But of course x is used over here. So how about I'm going to introduce something like this, that t, a new variable, is equal to 3x to the power of 3 minus 2x squared plus 7. Now, look, if I now substitute t for this expression, I'm getting a fairly simple function, y equals t to the power of 100. Look, even though power is bigger, differentiating this poses no problem. Okay, but what have we done over here? Look, what we have done over here is that we've introduced a new variable t, and basically we've got one function over here that is a function of t, and here t is a function of x. So again, you can think about it as f is a function of t, and that y is a function of t, and t is some function g of x. So how can I calculate the derivative right now? Look, from the chain rule, we're going to get that dy dx is equal to dy dt times dt dx. Okay, how much is dy dt? Well, dy dt is simply derivative of this with respect to t. So it's going to be 100 t to the power 99. Then we need to multiply it by derivative of t with respect to x. So we simply differentiate this expression, and we get that this is 9x squared minus 4x, right? Because 7 is 1. And look, we also know that t is equal to this. So now I just need to substitute back for t, and I'm getting that this is 100 times, let me just put this first, so times 9x squared minus 4x, and instead of t to the power of 99, I'm putting this, so 3x to the power of 3 minus 2x squared plus 7 to the power of 99. And look, even though this result was rather complex, we get that it is not that bad at this moment. Okay, so now that we know the mechanics of doing this, what is the easy way? Look, you don't need to always provide this entire substitution. It's pointless and it's too time consuming. So how would I do it? Look, the idea in this entire rule is that we can imagine it like we have two functions, like a function inside the function, right? So, okay, let me just write it like this. Okay, so, look, again, as I told you before, we read this as a command, differentiate with respect to x, whatever's in front. Okay, so this is our function that we need to differentiate. And now, how can I think about it? Look, I can think about it in this way, that here, we've got some inside function, and here, we've got some outside function. Because we can imagine that this is some number, like t, right? It is some variable, like t. So the rule that we get from this is that it is equal to derivative of the outside function times derivative of the inside function. Okay, how do we do it then? Look, it's now very easy. First, what is derivative of the outside function? We are imagining for a second that this is just x, right? We would get 100 up front times something, and then we would have to drop 1 from the power. And then we would have to multiply the whole thing by the derivative of this, which is 9x squared minus 4x. But of course, here we've got something missing, because for a second we were imagining that this is just x, and here we just need to rewrite 3x to the power of 3 minus 2x squared plus 7. Okay, so let's try another example and practice this. Let's practice this a little bit more. Okay, so again, let's just say that y is some function of 4x to the power of 5 minus 7x x to the power of 3 plus 2x to the power 1 over 2 minus 3 to the power of 50. Okay, let's now try to use the chain rule, but without resorting to an intermediary step. Okay, so what do I do first? First, I need to differentiate outside function that we've got over here. So this is going to be 50, that goes up front, times this entire expression to the power 49, because we dropped 1 over here. And now, all I need to do is to multiply it by the derivative of the inside function, which is 20x to the power of 4 minus 21x squared plus x to the power negative 1 over 2, and that's it. This is our result. Okay, and before we finish with the chain rule, I just want you to know that just like in a case of product rule, this rule can be very easily generalized to any finite number of functions. Okay, I'm going to show you this now first with the case of 3 variables. Look, imagine that we've got something like this. That we have some variable m, and this variable m is some function L of z. And z is some function of y, and then y is some function of x. Again, we can demonstrate a chain of causality over here. When x changes through function g, y changes. If y changes through function f, z changes. When z changes through function L, m changes. And now look, if I want to calculate derivative dm dx, what do I need to do? Look, I need to implement exactly the same chain as before, but now instead of 2, 3 times. Okay, and let's start actually from the back. Look, if x changes by small amount, y changes by small amount. If y changes by small amount, z changes by small amount. If z changes by small amount, then m changes by small amount. So what we need to do over here is simply to calculate 3 consecutive derivatives. So we would calculate here derivative of 3 different functions. L, derivative of L, as a function of z, we would multiply it by derivative of f as a function of y, and finally by derivative of g as a function of x. And look, I hope you can see that now we can easily extend this rule. If now we would have that we are not stopping here, but we would have that then some variable n is some function k of m, what would happen? The derivative dn dx would be equal to dn dm dm dz dz dy dy dx. So here we would have some 4 derivatives, right? Because here we would have another link in the chain of causality that's denoted by purple. And what do we would have here? k prime as a function of m times L prime as a function of z times f prime as a function of y times g prime as a function of x. So look, what you see over here is that in each case we are moving from one variable to another. We need to just introduce another derivative. So now, if the length would be 5 different variables, we would introduce fifth function, we would have 5 derivatives that need to be multiplied by one another. And look, I hope you can easily see that this rule can be extended to any number of any finite number of functions. Okay, so this is it about the chain rule. In the next video, we're gonna learn about inverse function rule. See you in the next video.